Hi all. We had an introduction lecture on high voltage engineering before, and I have given you an assignment to see what are the high voltage levels in India. Right? We discussed about we had an introduction, right? So from this lecture, we are starting the syllabus or the whatever will be covered in the syllabus. So in our first module, what we are going to learn? We are going to learn about the generation and transmission of electrical energy. That is the first thing that we will be learning, means what is meant by what is our power system network is. Then we will see voltage stress, then the requirement of testing voltages and DC generation. So mainly the high voltage DC generation. These are the major parts that will be covered in module 1. Okay. First we will have an introduction on generation and transmission of electrical energy. Then we will see what is meant by voltage stress, like what are over voltages and all. Then we will see what is the need of testing voltages, right? Like you might have heard high voltage testing. High voltage testing means applying high voltage. So what is the need of that and what kind of testing methods are there? That will be discussed in that section. Then we will explicitly see the high voltage DC generation. Okay, means in this whole syllabus we will see high voltage DC generation, high voltage AC generation and high voltage impulse generation. So first we will see high voltage DC, then we will get into AC in the next module, then we will go forward the same way. So let us see this section. So by this module what we are trying to identify is that what is the need of this testing voltages, or what is meant by high voltage testing. Okay, and of course the high voltage DC circuits. So about generation and transmission, if we say, as we know, like electrical energy is the one form of energy which is reliable compared to any other form, right? Which can be transferred from one place to another without much loss of power. That is the most important thing. So with the when we had this generator or dynamo, when people find out that, then afterwards we started making electricity, and we thought about what supplying it like we make electricity, like a generator unit is there, and we are supplying it to n number of consumers, right? So that system came into existence, right? You know about the story of Edison, Tesla and all, right? So and the generator unit, and we have the consumer unit. So this kind of a structure is already there for power system. So at first, as you know, like whether it is an Edison system or whether it is the first power plant or the power station, they were using the DC systems, right? So they were using this DC systems mainly. So DC systems were employed first, and that is what the thing is. Thing was what they were using low voltage. Really, it was very interesting. Like in the first DC system that was used for electrical lighting, they started connecting it in series. Then they understood the problem with series. What is the problem with series? If at all one lighting is gone, then the whole system is gone. So later what they did? Later they tried to they made it parallel. So such a big evolution is there in the power system network. If you search for like the story of electricity in YouTube, or if you Google it, you can find many interesting documentaries done by BBC and all. So that is your interest, and it will be very interesting to watch. Okay, like just like another movie. So this DC systems were employed at first, and the main problem was that they were identified to be not that reliable. Whenever like your generation and consumers are like nearby, then it is somewhat okay. But whenever your consumers are far away, right? Whenever your consumers are far away and your number of consumers are so high, then there was lot many losses came into picture. So that was a big problem when it came to DC systems, right? So that is why we went into what we went into AC system. AC system start you know the story. There was a war between Tesla and Thomas Alva Edison. So AC system came into existence after this DC system, and mainly we should say we should see that the involvement of Nikola Tesla as well as Westinghouse. So that is another man. So these people, the interesting part was that development happened in what AC generator, as well as the more important thing is the transformer. Transformer means what? You have a low voltage side. So in DC system we were not having any idea of converting it into high voltage. So using a transformer we were able to transfer power by varying what voltage, right? So you were able to vary the voltage. So whether we have to make it a higher voltage or lower voltage, that was possible. And later on we understood that AC system is more better compared to DC system. Okay, in terms of why it is, we will see. So again now we are going back to the DC system, because now we are able to control the DC using the power electronic devices that are available. Okay, so that is there, all that is there now. So this is what happened. Now let us see why we should use high voltage. As I said, with the advent of this AC system, and with after having a good transformer with us, that is when we started making into what, making it higher voltage and all. So why high voltage? Because one important part is what, because we are able to transmit we have to transmit the power over a long distance, right? We have to transmit the power over a long distance. So what can we do? Like you know that what power is given by what? Power is given by voltage into current, right? So power is given by voltage into current. And whenever your distance is so high, whenever your distance is very high, what will happen? Then your losses, like whenever your distance is very high, then the losses given by what? I square R, right? So losses in the transmission line is given by I square R. So whenever your distance is so much high, then the losses between two points, that also will become what? The losses happening in the transition line, that will become higher and higher. So under such condition, what a transformer will do, if we add a transformer, on one side of the transition line, and whenever it is generated, it is usually generated at low voltage only. So we will see why it is so. So once it is generated at low voltage, and when we convert it into high voltage, what will happen? In a transformer your power remains constant, right? So whenever you are converting from low voltage to high voltage, what happens is that your voltage is becoming higher, and at the same time what will happen to current will become lesser, but you get the same power, right? So means in order to get the same power, you can increase the voltage, so that what will happen, your current will decrease, right? So when you have a lower current value, then your transition losses will be lesser. That is why you are able to generate power at remote locations, and you are able to supply it to your consumers, right? Like if you consider a hydel power project, it can only happen in Idukki, right? Yeah, or near Periyar. We cannot keep it inside inside a city. Like we cannot keep it inside Cochin or any other place. But the power you can transmit over long distance to here, right? So that is possible because it is transmitted at a higher voltage, not at the voltage which is at which it is generated. Okay, similar is the call or any other power, like wind power units we have to keep where wind is available, right? Solar power units we have to keep where you have more solar radiation. You cannot keep where you need to use that. So that is the major difference, that is the requirement, right? So whenever our electricity demand increased, depending on the increase in demand, we had to make we had to generate power at remote location, and we had to send it to long distances. So because of that, we went for higher voltages. Whenever your voltage is higher, then what? Then you have high power transfer capability. Like you think of a system where you are using low voltage, and your power transfer capability is higher, then the current will be higher, right? So in order to reduce the losses, what you have to do, you have to increase the radius of cross section of the conductor. That again is a problem, right? In order to increase the current, you have to increase the radius of cross section of the conductor, so that your losses will be lesser, right? R is equal to rho L by A. So since area cross section is inversely proportional to resistance, so you have to do that. That is one condition. Again, another interesting thing is that when you are transmitting your power over long distances, it is not only the electrical parameters that you have to see. You also have to see one more thing, right? Whenever current passes, there will be temperature increment in the transmission line. So if it cannot be so much high, understood? So there is a limit for the temperature increase also in a transmission line. So these all factors we have to consider. But when you are making it to higher voltages, then you are able to transfer the same power at lesser current. So one way of seeing it is like that. So if we transfer power, a basic equation is like what, V square by R, right? So similarly here, if I the power transfer capability, that is proportional to the square of voltage. So whenever you are increasing the voltage, your power transfer capability also is increasing by what, square of the voltage. So that is what is meant. So this shows the curve between what the voltage, this way it is what, this way it is the voltage, and one second, let me take it out. This is the voltage, and on the y axis you have what, you have the power in megawatt. Okay, this is the power and this is the voltage. So when I am like, when you have 400 kV system, then your power transfer capability is what, 640 megawatt. When it is 700 kV, 2000 megawatt, then it is 1000 kV, 4000 megawatt. So you can see that it is like an exponentially increasing with what, with the voltage level. We already discussed about what are the voltage levels available in India and all, right? So why we went for this higher voltage levels is quite understandable from this figure, right? As your voltage level increases, then your power transfer capability is also increasing to a higher extent. So that is, I think you are able to understand that here. What are the voltage levels that we have? Okay, in a power system we have several sections like generation, transmission, distribution, and consumer, right? Power generation, transmission, and distribution. So the subject you are already studying in this semester, I believe, and there you will see all these things. So an interesting part is that like why we are not able to generate voltage at higher voltages directly. Main point here is the insulation. The limitation comes from insulation. If at all you are generating voltage at very high voltage, then you have to give the insulation also to that extent, right? Like if you have a 1 thickness of mica or rubber with you, and let me say it is able to withstand 25 kilovolt. But when you have to when it has to withstand 100 kV, you have to have a rubber of like 4 thickness. So when such a need arises, then your dimensions, like your insulation thickness or the dimension, is increasing. So your generator size will increase. So above some size you cannot design a generator in an efficient way. So that is why your generation is always at lower voltage, and we have different generation levels. Like you can see here, small generators means those generators which are generating voltages what levels, for 40 volt, 3.3 kilovolt, and 6.6 kilovolt. Then there comes what, somewhat medium and high power generators, let you can say high voltage generators. Another one is like 21.5 kV and 33 kV, right? So there what is happening, it is like 500 megawatt and 1000 megawatt capacity. Okay, like I think you are able to understand, like this is very high capacity. Other generators, the first set is like very small generators, but and normally most of the generators are of what type, 11 kV generators, 110 and 220 megawatt, right? Okay, so like if you see the smaller power plants, they will have this 11 kV generator, which is having the power capacity of what installed capacity will be 110, like 110 and 220 megawatt. But when it comes to like a super thermal power plant, we have a super thermal power plant like up to like, in the range of this 1000 megawatt and all. There we have this huge generators. Okay, we have this huge generators like 21.5 kV or even 33 kV generators there. They are huge. Like if you go and see the winding and the stator winding installation, you will be astonished. Okay, even the rotor winding, like inside a synchronous generator, you have a field winding. So in that field winding, in order to cool, that field winding means what? That is how you produce magnetism, right? Like in a dynamo, you have what? You have a coil and you have a magnet. You have a magnet. Similarly, in synchronous generator, the field coil, right? The field coil is what, which is what generating the magnetization current, right? So that generator rotor bars, they are like getting cooled with liquid hydrogen. So such a huge system or such a sophisticated system is needed. So that is about what generation unit, and normally we generate at a lower voltages. Once it is generated, then what we will do afterwards, we will apply our transformer, right? Then we have our transformer to convert it into any higher voltages without loss of power, right? So what is the efficiency of a transformer? You know well, right? So transformer is used for, when to what do what, to have long range transmission. So that is what our transmission system is doing. And such AC transmission system levels, this 11 kV, what we do, we change it to like 110 kV, 132 kV, 220 kV, right? These are the levels of transmission voltages. Okay, so normally from a generator, what our normal generator, conventional generators, what this is what we do: 110 kV, 132 kV, 220 kV, 380 to 480. Like you already have a list of what are the voltage levels in India, right? So 765 kV is quite operational now, and even 115 kV, 1150 kV also exists. Then apart from that, as I already told you, that now first we went from what, we went from DC to AC. Now sorry, DC to AC. Now we are again going back to what, DC transmission. Why? Because as I said, we before we were not able to, like DC was not that flexible without losses. So now that is possible with the advent in power electronics, and we have like from plus or minus 100 kV to 500 kV or even up to 800 kV, we have high voltage DC lines. Okay, that which are used for the same purpose, like which are having higher power transfer capability, and frankly which are having more flexibility in power transmission. So that is there. Maybe you will learn in some other section. Okay. Now once it is generated, now the third part, transmission means what? Now from the remote generation units, you are transmitting it into long distances. So that has happened. Then your next section comes to what? Then your next section is the distribution section, where your power is getting distributed into consumers. So there you have different levels, like what, up to 66 kV, 440 volt, 3.3 kV, 6.6 kV, 11 kV, 33 kV. This all you know, right? Like 11 kV transformers, you already I think you are seeing, right? When you go out on your side, whatever transformer, three-phase transformer you see, that will be one 11 kV transformer. Okay, and we have a 66 kV. 66 kV substation nearby our college, right? And I think you know, try to identify what is the voltage rating of what our Kanyambeta substation, right? So these all things are nearby us, and I believe you might have visited substation, or it will be good if you visit. So these are the levels. So in distribution again, it comes, or when it comes to the consumer level, you need a lower voltage again, right? So in transmission section, what is our need? We have to transfer power over long distances, right? When it comes to transmission, we have to transmit power over long distances, right? So that is our interest when it comes to the transmission region. But when it comes to, again comes back to consumer, you don't want those high voltages. Like think about using a 110 kV iron box at your home. Then your iron box will look like will have a size like what you cannot imagine. So you need it again to reduce the voltage level, and even it is dangerous. Like high voltage means even 440 volt is considered as high voltage. by different levels at different countries. So because that is dangerous, so you need lower voltages. So there we have this 110 volt 220 volt systems, right? So 110 volt is what used in US, and 220 volt is followed in India and other countries. So that things are there. And in consumer, I want to note here one more thing, like the railway traction. You can see the railway traction voltage level is 25 kV single phase. So that is something that you can see, because that is a big consumer, right? So that is one thing you can be aware of. So these are the voltage levels in that we are using, and why we are using, I think you got a picture, right? So basically this levels, when it comes to generation, there is a limitation due to what? The insulation, because when the insulation dimension increases, then your generator size increases, which is not, which we cannot afford. So and in transition we are looking for higher and higher voltages, and that demand is ongoing, like this 765 or 1000 kV. Why we are going for that? Because our electricity demand is increasing to that extent, so that our power transfer capability also needs to be improved. So that is why. Now let us see voltage stress, right? So when this I took material science for you, and that time itself we know, like whenever we apply a voltage, then it is voltage stress. So the really what we mean is the electric field density inside. Okay, so when we apply a stress, there is a stress in that material. So if it is for a longer time, it will cause deterioration. So basically, I think you are aware of the line voltage and phase voltages and how they are related, right? Phase is equal to what? VL by root 3. And which voltage we usually say, like when I say 11 kV system or 33 kV or 66 kV, which voltage I am mentioning in power system network? Is it phase voltage or is it line voltage? It is line voltage, and that is what we call as a nominal voltage. Nominal voltage is the phase to phase RMS voltage. Okay, not phase to ground, not phase to ground or not phase to neutral. It is what the phase to phase RMS voltage is termed as what? The nominal voltage. That is the one thing you should understand first. Then let us see, if it is nominal voltage, what is the maximum system voltage? Maximum system voltage is frankly what? It is the maximum rise of the RMS phase to phase voltage, right? So inside a system, what this is not Vp, sorry, this is Vm, right? Inside a system, if you have this VL, then what? Root 2 times VL will be what? The maximum system voltage, right? So that will be maximum system voltage. But when this is what is we are going to say, when we say voltage stress, we mean that whatever nominal voltage your equipment is designed, or for whatever maximum system voltage is defined, it is designed, more than that some voltage is coming. So how do we define that? Like if you take an insulator, like or an overhead transmission line, if you see an insulator, you can see it like this. So if you have a pole like this, and you have an insulator here kept like that, and your transmission line is going, your one phase is coming here, right? Your one phase is coming here, and the point here, this point on the other side, that is what? That is the ground potential, right? So always along an insulator, or even along any equipment, whether it is a lightning arrestor or any other equipment, always the phase neutral voltage will come along its terminals. So your insulation has to withstand what? It is not the phase to phase voltage or the line voltage that you have to withstand. You have to withstand what? Or what is applied, or what is the voltage that's really on the insulator? That is the phase to neutral voltage. Understood? The VP, phase to neutral voltage, is what? This usually comes across the insulator. Okay, then what will be the maximum? If let me say, sorry, let me say that this is your, okay, this is your system voltage. Okay, when I say phase voltage, that is the RMS value. So root 2 times the phase voltage will be what? The maximum voltage. Okay, if your voltage, if the applied voltage goes above this maximum voltage of the maximum value of phase voltage, then we say that we have an over voltage. I think you understood. Okay, like VL by root 3 means what? VL by root 3 means that is line voltage divided by root 3, which is the phase voltage. Root 2 times of that means what? That is the maximum value of phase voltage. Above that, if we put some more stress, if we apply more voltage onto an insulator or an equipment, then what we say? We say that it is over voltage. Okay, so that is what is meant by voltage stresses. Okay. This overvoltage, it can occur due to different reasons. Okay, so the power system overvoltage are classified or categorized like this. It can be due to what? It can be due to it can be internal overvoltages as well as external overvoltages, right? So the internal overvoltage means they are occurring due to the changes in the operating conditions of the system. Understood? Like we are switching on or switching off some load in power system network, or we are adding a capacitor, or we are taking out a capacitor. When such things happen, then we have this internal overvoltage. And external overvoltage means what? That is something happening due to the atmospheric disturbance. Means something that which is not in our hand. Okay. Such things we call as external overvoltage, and one such thing is what? The lightning over voltage, right? Lightning is the one form of electricity, right? So this is the classification of power system over voltages. Internal over voltage means those over voltages when it happens due to the changes in the operating conditions of the system, right? It's the changes in the operating conditions of the system, and the external over voltages are caused by atmospheric disturbances like lightning. So this is the classification of over voltage. And in that, what is meant by temporary overvoltage? Temporary overvoltage means those are temporary, as the name suggests, and which will occur for long duration. Okay, so such things are called as the temporary overvoltages. They take and they usually take the form of this undamped or slightly damped oscillations. Means it will be there for some time. It is not getting directly damped, so some weakly damped. In general sense, this term will include all overvoltage of frequencies which are what? Lesser than 500 hertz. Means it is something occurring at a slower pace. So that is what is meant by temporary overvoltage. And we have an iterative standard for that, and this is a definition. An oscillatory phase to ground or phase to phase overvoltage that is at a given location of relatively long duration. Understood? Which occurs at a given location for relatively long duration, seconds, even minutes, and that is undamped or weakly damped. That is what is meant by temporary overvoltage. And what are the causes of this temporary overvoltage? Let us see. Okay, the what all things causes the temporary overvoltage? One is called as load rejection. Load rejection means you had some load, suddenly it is dropped, or your load is gone in the system. Okay, such cases you can have a temporary overvoltage. You will see how. Then whenever you have a fault, ground fault means one of your phase is getting one of your phase is having a connection with the ground, like a tree branch has fallen and it is having a ground connection. So that is what is phase to ground fault. Okay, under such condition that also can lead to over voltage. Then what? Then Ferrandi effect. These are all load rejection, ground fault, Ferrandi effect. Then ferromagnetic resonance. This thing you will be going to learn in much more detail in power generation, transmission, and protection, PGTP, right? So in that subject, but we will have a small introduction to that here. So first let us see what is meant by load rejection. So when a transmission line or a large inductive load that is fed from a power system bus, okay, that is suddenly switched off. Let me say it is suddenly switched off. The system frequency has a tendency to go up, and the bus voltage will rise temporarily till the steady state is reached again. Understood? Means when a bus is suddenly switched off, system frequency will become a bit more high. Like you think of it like this. You have a generator and you have a prime mover. Where what your mechanical energy is converted, or there is a mechanical electrical energy, there is a balance between both. When your load is taken out, it is like what the mechanical power is more and your electrical output is lesser. The demand is lesser, right? You have a generation, but your demand is comparatively lesser. Then what will happen? Then it is like on the prime mover you have uh, lesser effect, or that is why it will start rotating a bit more faster. That is why your frequency will increase. So similarly, if let me say if this is the this is the sending end voltage is E, and you have this is your receiving end, and once you have a load rejection. Understood? You have your load is rejected. What will happen? Means in a transmission line, I don't know whether you reach to this extent, but in the transmission line you have this reactance. Okay, means this is what, this is the impedance or the reactance of this network, and you have what, you have this shunt capacitances. Shunt capacitance means whenever your transmission line is running, transmission line and ground, between that you have a capacitance. Okay, normal cases your load reactance or your load impedance will be very high, and because of that your sending end and receiving voltage will be similar. But under a condition when your load is rejected, or when you do not have any load, what will happen, most of this thing will what will be active, this xc will be that xc will be higher compared to this xs value. So your if you take the voltage, what you will get, voltage is equal to E into xc by xc minus xs, right? The voltage division formula, E into whatever be what here xs and xc will come in series, right? So xc divided by xc plus xs, right? But since xs and xc since they are opposing, that is why what we have xc minus xs. So definitely one thing you can understand here, this voltage V will be higher compared to E, because xc by xc minus xs, xc minus xs will be what, it will be definitely lesser than what, xc. So because of that this will be what, some xc divided by lesser than that. So because of that you will have this voltage to be higher. So this is how due to load rejection you have increase in voltage. Now the another thing is that earth fault. Like here let us consider that phase A, this is your power system network, you have three phases A, B, C, and your phase A is what, there is an earth fault. Earth fault means what, your phase A potential, this line which is at a potential of, let me say, AT or VA, that is what, that is coming to ground, right? When like it is getting short circuited to ground, so what is the thing going to happen at first? Definitely a high current is going to flow, right? Definitely a high current is going to flow through this phase A, right? Through this phase A high current is going to flow. Whenever you have a high current flowing through this, I think you know about mutual induction, right? So what is the total what is the total voltage in this line? In this B phase, what will be the total voltage? V will be equal to E plus L, means L di by dt plus M into d I dash by dt, right? So due to the mutual coupling between this A phase and B phase, definitely a voltage will be a high voltage, because due to earth fault this is already at some potential A, and when it is short circuited to ground, a high current is flowing. So your B phase and C phase will have higher voltages. So that is another cause of having over voltages, which will come on to what, which will come on to the insulators to which they are attached to, right? So that is about the earth fault type of over voltage. Now let us see Faraday effect. Faraday effect also is quite similar to load rejection. Let me say, when your when your system is like lightly loaded or unloaded, and under such case, what will happen? Then, as I said, you have this line resistance and reactance, right? And you have the shunt capacitance also. The equivalent can be shown as here. Okay. So under light load or no load condition, what happens? Already, in order to reduce the losses, our transition line resistance and reactance, what inductive reactance, they are kept to be what, they will be small, right? So when your load is not there or it is unloaded, what will happen? Then this capacitance part, that will become more dominant. So because of that, you have a more capacitive current. Like if you take in the phasor diagram, ER is considered as the reference. ER is considered as the reference. And what, since the circuit is more capacitive, your total current will be what, probably IC only, or smaller, very much nearby IC. So your IC R EQ, but what the R EQ part will come into what, the IC part, or your sending in voltage will be lesser as shown in this phasor diagram, and your receiving voltage will be higher. Again, you will learn more about this in your PGTP, so I am avoiding all the discussion here. Okay, so Faraday effect also will cause the increase in voltage level in the receiving. So again, that is another cause for having what kind cause for having what, for having over voltage. Another thing is the temporary over voltage due to ferromagnetic resonance. Like in an electrical system, you have this capacitors and inductances all along, right? You have shunt reactor, you have transformer, you have lightning arrestor, you have the whole capacitor bank. Okay, so all this when they come, and let me say sudden switching operation happen. Under such conditions, this L and C circuit it is, so resonance can take place, right? So at such conditions, the ferro resonance, ferromagnetic resonance or the resonance can take place. So that also can induce what? That also can induce higher voltage levels in this system. So in this lecture, we have learned about the power system network, and we also saw different like what is meant by voltage stress, and we saw the reason for having voltage stress, right? So I hope you understood the parts in this lecture. If you have doubts, we will discuss in the next live session on Wednesday, sorry, on Saturday or Friday, right? So whenever the next time, as per timetable. And then the next lecture we will see about switching over voltages and lightning, and see what is the need for this testing voltages. Once we cover that, we will move on to DC voltage generation. So as I told in the last class, your attendance will be considered from the note that you are going to upload in the Google Classroom for now. So just see this video and write your notes and upload. Okay, thank you.